In the lectures we've been looking at the distribution of the OLS estimator. Most of the results here are actually really rather simple, but they involve quite a lot of algebra. So what I've done is prepare this video to supplement the material in the lectures and go through some of the algebra in a little bit more detail for those of you who are interested. But let me start off with a central problem. We want to estimate the regression equation y equals alpha plus beta x plus u, and we've developed the OLS estimator of the slope coefficient to be beta hat equals the sum of xi minus x bar, yi minus y bar divided by the sum of xi minus x bar squared. And we can interpret that as the ratio of the sample covariance of x and y to the sample variance of x. Now the central result we want to derive is the distribution of that estimator, because that estimator, being a function of random variables, will itself be a random variable. So there are two sets of assumptions that are critical here. There's the Gauss-Markov assumptions, which we need to show that beta hat is the best linear unbiased estimator. But that's not quite enough to derive the distribution of beta hat. We also need to make a specific assumption about the distribution of the errors if we are to derive its distribution. The assumption we make is that the errors follow a normal distribution. So if we combine the Gauss-Markov assumptions with the assumption of a normal distribution for the errors, we can show that beta hat follows a normal distribution with mean equal to the true population parameter beta and variance equal to sigma squared u, which is the variance of the error term, divided by the sum of xi minus x bar squared. So this is a standard result that if we take a linear combination of normal random variables, we end up with a normal variable. Okay, so now I'm going to go into a little bit more detail about how we get to this end result here. This is what we're interested in explaining. So let me start off with the definition of beta hat. So here we've got our definition of beta hat, and I can show that I can write the numerator of this expression as the sum of xi minus x bar y rather than yi minus y bar. Why is that? Well, if I expand this numerator, then the term y bar times the sum of xi minus x bar will be identically equal to 0. And that's because of the definition of x bar as the mean value of x. So I can now take this form here with yi and substitute for yi from the original equation and get beta hat equals the sum of xi minus x bar multiplied by alpha plus beta xi plus ui divided by the sum of xi minus x bar squared. Again, let me expand that numerator here, as in this line here, and you see that the numerator, we've got the terms alpha times the sum of xi minus x bar plus beta sum of xi minus x bar xi plus the sum of xi minus x bar ui. Now the first of those terms drops out immediately, again because if we consider that, we've got alpha multiplied by the sum of xi minus x bar, which must equal 0 again by definition of the mean of x. Now consider the term the sum of xi minus x bar times xi. Well, if I multiply through there, I'll get the sum of xi squared minus n x bar squared, which again is just identically equal to the sum of xi minus x bar squared. So that again I can make use of this. So if I substitute those two results in, then I can simplify my expression for beta hat and write it as beta hat equals beta plus the sum of xi minus x bar ui divided by the sum of xi minus x bar squared. And that's the form that's most useful to me for proving my results. Basically, I've gone quite a long way already in deriving my end result, because I've shown in this line here that beta hat is a weighted average of the equation errors, the ui's. If the equation errors follow a normal distribution, then we're taking a weighted average of normally distributed random variables, and by a standard result in statistics, any linear function of normal random variables is itself normally distributed. So we've already established that the beta hat follows a normal distribution. And we know that for a normal distribution, it's characterized by two key parameters, its mean and its variance. And so what I need to do to determine its distribution is find the mean and the variance. And that's where the Gauss-Markov assumptions start to come in. So first of all, let's concentrate on the mean. To derive the mean, we take expectations. So we take the expected value of beta hat. Well, the expected value of beta, the first term is just beta because that's not a random variable. But the second term here, if I make Gauss-Markov assumption 4 that the x's are not random variables, then the expectations operator doesn't apply to the x's, or alternatively I can take the x's outside the expectations operator, and I can write this term as the sum of xi minus x bar times the expected value of ui divided by the sum of xi minus x bar squared. So what allows me to take those x's outside the expectations operator is the fourth Gauss-Markov assumption. Now, it follows that if I now consider Gauss-Markov assumption 1, that the expected value of ui equals 0 for all values of I, then it immediately follows that the expected value of beta hat equals the true value beta. So what's interesting about this is that I only need to make use of Gauss-Markov assumption 1 and Gauss-Markov assumption 4 in order to establish that the OLS estimator is unbiased, that the expected value of beta hat equals the true value beta. So I don't need to make use of assumptions 2 and 3, and as a result, the result of unbiasedness is not sensitive to whether or not the errors are correlated with each other or whether or not the variance is constant. I can relax those assumptions and still have an unbiased estimator. But when it comes to deriving the variance of the estimator, it's convenient to make those assumptions. So if I take now the variance of the estimator, that's defined to be the expectation of beta hat minus its expected value all squared. We've established that the expected value beta hat equals the true value beta, and so it follows that the difference between beta hat and its expected value, if I just go back one page, is given by this expression here, the sum of xi minus x bar ui divided by the sum of xi minus x bar squared. So in order to derive the variance, I need to take the expectation of that quantity squared. Now that's where the second and third Gauss-Markov assumptions become quite convenient, because from Gauss-Markov assumption 2 we've got the expected value of ui multiplied by uj is equal to 0 for values of I that are not equal to j. So all the cross product terms, the ui uj's, will drop out when we take expectations. In addition, the expected value of ui squared is a constant by virtue of Gauss-Markov assumption 3. So the variance is constant of the error terms. Again, that's going to be convenient because it will simplify the expression that we get. And in fact, if we now make use of these assumptions, as well as Gauss-Markov assumption 1 and Gauss-Markov assumption 4, of course, we get an expression for the variance which takes this form here. So I square everything here and then take expectations, and we get the sum of xi minus x bar squared multiplied by sigma squared u divided by the sum of xi minus x bar squared all squared. Now of course I can cancel the numerator and the denominator here. I can divide through by the sum of xi minus x bar squared and write this as sigma squared divided by the sum of xi minus x bar squared. And that's the result I was aiming to get from the start. So we've therefore established that if the Gauss-Markov assumptions hold and if the errors are normally distributed, then first of all, OLS is the best linear unbiased estimator. It's unbiased and it has the lowest variance in the class of unbiased estimators. And secondly, if the errors follow a normal distribution, then the estimator also follows a normal distribution. And we have this result here, that beta hat follows a normal distribution with mean equal to the true population parameter beta and variance given by this expression here, sigma squared u divided by the sum of xi minus x bar squared. And we're going to make a lot of use of that expression in deriving test statistics for hypothesis testing using the linear regression model.